So we've got a diagram that we're going to use for the whole question and some information. So let's read that information. Sarah stands at the end of a diving board of a total length of 4 metres. Okay. The diving board is fixed to 2 supports A and B, which are 1 metre apart. The mass of the board is 10 kilograms and Sarah's mass is 50 kilograms. Assume the mass of the board is evenly distributed. Now that's quite an important assumption, and it will likely help us. So, calculate the torque exerted by Sarah around support B. Okay, so what do we need for a torque? We need a force and we need a distance. All right, torque is a turning force applied at a distance. Okay, so what is the force that we use? Well, we use the weight force, okay, or the weight force of the object. So in this case, the weight force is whatever mass we've got times gravity. So because we're looking at Sarah, the force of Sarah, we're going to use Sarah's mass of 50 kilos times by our gravity of 9.8. And that will give us 490 newtons. Okay, so that's the weight force. All right, the next step is to work out which distance we need to use. So the distance is going to be from where the weight force is happening to our pivot point, so to point B. So our distance is going to equal 4 metres minus 1 metre, all right, which is this distance here. So our distance is going to be 3 metres, all right. We can then just put that into our equation. And we should get an answer of 1,470 newtons. Now, we need to think about those significant figures again. So, what have we used? We have 2 significant figures here and 2 significant figures for our gravity, and we also have 2 significant figures for our distance. So our answer must also be in 2 significant figures. So we go from 1,470 to 1,500 newtons, 2 significant figures. Okay? So Newton meters. Remember that torque is a force at a distance. All right, that's our A. That's just a simple achieved. Okay, right. What is the direction of the force supplied by support A? So we're now looking at this support here, support A. What direction is that going to be? Give a statement about which direction, and then here explain why. So give some reasoning. This is slightly counterintuitive, this one, all right? But basically what we've got is this is our key sort of turning point here, all right? So Sarah, weight force is going down, okay? The board will also have a weight force going down. So everything is turning around this point, all right? What this point must then be doing is it must also be providing a force downwards so that this board doesn't flip off when Sarah jumps. So the force of support A is downwards. All right. This is because, so we have a torque here with Sarah, we have a torque here of the board's mass or the board's weight force, all right? So both of those are in the clockwise direction, all right? For this to be in equilibrium, we need a torque in the anti-clockwise direction. All right, so that is provided by support A. All right, so let's state that. The torque at A must be anti-clockwise to counteract the clockwise torques produced by Sarah and the board. So that this sentence here is our explanation for why it has to be downwards. So here's question C. The diving board sags or bends 0.050 of a metre when Sarah stands still at the end. Okay. Calculate the spring constant of the board, and we're assuming that the board is acting like a spring. So we need to look at our equations here. All right. And this F equals negative kx is going to be the equation that we use. This is Hooke's law, and this is the one we use when we're looking at springs. Okay, so let's write that equation down. F equals negative kx. All right, but we're actually not interested in F. We are interested in k. All right, so remembering that x in this case is a distance. All right, we're wanting to know what k is. Okay, now in this instant we don't actually need the negative. Okay, because we're not interested in direction at this point. All right, that is what the negative is there to show us. So let's rearrange. So we're wanting to have k by itself, which would mean that the force is divided by x, which is the distance or the displacement. Okay, so do we have a force? What force is going to be the force in this situation? All right, so the displacement is caused by Sarah standing on the end, which means that it's her weight force that we're going to be using for this equation. All right, so we calculated that on the previous question as well. All right, so you can just use that number straight away, or you can just do 50 kilograms times by 9.8 in place of that x, F, and then divide by x, which is your distance here of 0.050. Is an answer of 9,800 newtons per metre. So make sure that -1 is in there. All right, 9,800 newtons per metre. And with this one, we're already at two significant figures. That's all the detail we've got. That's all the answer. That's all the detail that our calculator is showing, so we don't need to do anything more from there. So please be careful that you use the weight force, so mass times gravity, not just the mass. All right, question D. So Sarah jumps up and then lands on the board, depressing it or displacing it by a further 0.2 meters before she dives. Okay, calculate Sarah's speed when she lands on the board, causing it to depress by a further 0.2 meters. Let's have a think. There is a clue in the title. All right, this question is about energy, but there's also a clue in the fact that we've got some distances here, but no times. Okay, so we're not going to be using any kinematics or any of those kind of equations. All right, what instead we are looking at is energy. Okay, so remember that we've got two types of potential energy. We have our gravitational potential energy when we lift something up off the ground or off a surface, all right? And we have this elastic potential energy, or potential energy that we hold in things like springs. Okay, so that's the one that is going to be useful right now. So let's start with that. EP, the elastic potential, is equal to half the spring constant times the displacement squared. Okay, so we've worked out our K from the previous question, so that's easy, we can just put that in. But what is the X that we're going to use? All right. Now the X that we're going to use is the total displacement. All right. So when Sarah is not standing on the board is at this level. All right. When Sarah is standing still on the board and before she jumps, it decreases by 0.050 meters. All right. And then, once she has jumped and then landed, it decreases by a further 0.2 meters. So the total distance from the sort of equilibrium point when there's no one on it to the final point is actually 0.25. So adding these two together. All right, and then we're going to square it. So what we should get is 306.25 joules. Okay, so that's the potential energy. Then we need to state that potential energy is equal to kinetic energy, all right? And kinetic energy is the one that has the velocity in it. So EK equals half mv squared. What we need to do is we need to rearrange this equation to get velocity by itself. All right, so we're going to do that up here. I will rewrite our starting point. Okay, so the easiest one to get rid of first is this half. We're just instead timesing it 2ek equals mv squared. All right, and then we're going to divide by m to get v squared by itself. So 2ek divided by m is equal to v squared. And then hopefully you can see that our last step is to square root that, and we'll get velocity by itself. Okay, so all we now need to do is plug in our numbers. We have Sarah's mass from previously. We've worked out the energy that we're going to use, so we could write EK as EP and it would be the same situation. All right, so V equals 2ek divided by m and then square root that. So we're going to have 2 times 306.25 divided by 50 and then square root that whole thing, a velocity of 3.5 meters per second once she lands on that board. Calculating this or having this idea gets you an achieved. Getting both this and this gets you to a merit, and actually getting you to the end gives you an excellence.